When you think of ice, you probably picture something static, right? A permanent feature of our planet's coldest, most remote places. But what if I told you it's not? What if it's actually a time machine, a flowing, dynamic archive of Earth's entire history?
Okay, just picture this for a second. What if you could actually travel hundreds of thousands of years into the past and take a real, actual sample of the air from the last ice age? What stories could it tell us?
I know. It sounds like something straight out of a sci-fi movie, but it's totally possible. And the secret? Well, it's locked away, frozen deep inside our planet's massive rivers of ice.
All right, so how exactly does this time machine work? It all starts with a fact that sounds a little, well, wrong. The fact is, glaciers are basically rivers of ice.
Yeah, they aren't just giant frozen blocks sitting still. Glaciers are these immense rivers of solid ice, constantly flowing from high elevations down to low ones, all under their own colossal weight. It's a lot like a river of water, just moving in super slow motion.
Okay, but wait, how can something solid actually flow? To really get the whole time travel part, we've got to pop the hood and look at the engine, the mechanics of how it all moves.
So it all comes down to this constant balancing act. Think of it like a bank account. Up high in the accumulation zone, you're getting deposits. That's snowfall adding mass. And way down at the bottom, in the ablation zone, you have withdrawals, ice melting or breaking off into the ocean. The glacier flows to try and balance the books, moving ice from the rich part to the poor part.
So what's the engine driving all this? It's a force called shear stress, which sounds complicated, but trust me, it's not. It's literally just the crushing weight of the ice itself, on a slope that gets things moving. I mean, think about it. You've got the density of ice, times gravity, times thousands of meters of thickness. That's a huge amount of force pushing the entire system forward.
And all that stress, all that pressure makes solid ice do something pretty wild. Under all that weight, individual ice crystals actually deform and slide past one another. It's a process called ice creep. The best way I've heard it described, imagine the entire glacier flowing like a super thick, super viscous fluid, kind of like very cold honey.
And this is a perfect snapshot of what that looks like in the real world. Here, scientists are measuring the glacier's energy budget. How much sun is it soaking up versus bouncing back? Because that energy is what fuels the whole system we've been talking about, that delicate balance between snow piling up and ice melting away.
Okay, so we've established that glaciers are always flowing, which begs the question, right? How can you possibly read a history book when the pages are always moving? Well, that's where the incredible science of drilling through time comes in.
This really is the key question, isn't it? If the whole thing is stretching and deforming and flowing, how in the world does it keep a perfect year-by-year historical record? You'd think it would all just get mixed up into a big, icy scramble.
The answer is actually pretty simple and really elegant. The flow is layered. So every year, a new layer of snow falls, burying the last one. That snow gets compressed into ice, and those layers then flow down and out. But here's the magic. They stay in order. They keep their chronology, almost perfectly preserved. It's almost exactly like looking at the rings of a tree.
So to read this amazing record, scientists do exactly what you'd think. They drill. They drill deep into the massive ice sheets in places like Greenland and Antarctica, and they pull up these long cylinders of ice we call cores. And some of these cores are just mind-bogglingly long. We're talking over 3 kilometers. That's almost 2 miles straight down to the bedrock.
So what's inside these frozen libraries? It's an absolute treasure trove of information. You've got these tiny, perfect bubbles of ancient air trapped inside. You can see distinct layers of volcanic ash from eruptions thousands of years ago. There's even dust that blew in from other continents. And, most importantly, you have chemical fingerprints that tell you the temperature when that snow first fell.
Right, so each of those little clues tells a piece of the story. But how do scientists actually read it? How do they translate all that data? Well, that's the incredible art and science of decoding the ice.
This table, right here, is basically the Rosetta Stone for understanding past climates. So you measure things called stable water isotopes. That tells you the temperature. You analyze the gas in those trapped air bubbles, and bingo, you've got a direct sample of the ancient atmosphere. CO2, methane, the whole deal. You can even measure the electrical conductivity of the ice, and that can tell you about massive volcanic eruptions from the past.
So just how far back can we go with this stuff?
Well, in a place like Greenland, these ice cores give us a super detailed, year-by-year climate history that goes back more than 100,000 years. That's incredible. It takes us all the way through the last ice age and even into the warm period that came before it.
And when you put all of this research together, one thing becomes incredibly, undeniably clear. There is this remarkable lockstep relationship for hundreds of thousands of years, as far back as we can see. When CO2 goes up, temperature goes up. When CO2 goes down, temperature goes down. They rise and fall together. The connection is it's fundamental.
Having this deep time perspective is just invaluable for understanding what's happening right now, because what these ancient records show us, well, it points towards a potentially unstable future.
One of the scariest and most important things the ice has taught us about is the idea of tipping points, and a huge one is something called marine ice sheet instability. Now, this is a major concern for huge ice sheets, like the one in West Antarctica, because they're sitting on land that's actually below sea level.
Okay, so what really matters here is the shape of the ground underneath the ice. So look at the left. If the land slopes uphill as you go inland, a retreating glacier moves into shallower water. That creates friction, it slows things down, and it can eventually stabilize. But look at the right. This is the situation in West Antarctica. The bed slopes downhill, so if it starts to retreat, it moves into deeper and deeper water. That means the ice flows faster, which causes it to retreat even more, which makes it flow faster. You see? It's a runaway feedback loop.
And that right there is why this ancient ice record is so incredibly important. It's not just history for history's sake, it's like a user's manual for planet Earth. It shows us with chilling clarity that our climate system has these critical thresholds, and if you push it past them, you can trigger changes that are incredibly fast and potentially irreversible.
For hundreds of thousands of years, the ice has been quietly recording its story, and now we've finally figured out how to read the language it's written in. So the question it leaves us with is pretty simple, but it's a big one. The ice has told us its story. What are we going to do with that knowledge?